So, I'm super excited to be here, everybody. This is amazing. My name's Matt Katz, and I am a ceramic materials nerd. I have taught materials now for 16 years. I started off at my home base, my alma mater, Alfred University, where I studied under the art department under John Gill, and then in the ceramic engineering department under a wonderful man by the name of Bill Carty. And I made it my practice to try to translate ceramic engineering into English. And I hope I do an okay job of it. Over the years, my life changed. And at one point, my wife and I moved out of Alfred. We'd been living there for a long time. And as part of that, I started doing online teaching. And through Alfred University, we started offering courses to everybody. And I see a few familiar faces out there of people that have taken these online courses with me of just glaze calc for everybody. And as part of that, I started getting students all over the world. Students all over the US, all over Canada, Asia, Europe, South America, Australia, just everywhere. And it became this really amazing dialogue because the internet brought us all together. And I had several students that the conversation just kept going, and it spilled into Facebook and into chats and into friendships and into discoveries. And so over the years, some of our students who are up on the dais with me and I have just continued to do research, to explore glazes, even though we all lived in radically different places. Kiara in the middle here is the first time I met her was yesterday, but I've talked to her for years. Sue I met for the first time last year, and Peter as well. And it's turned into this amazing collaboration where we can take ideas and time that some people have and some people don't, and facilities that some people have and some people don't, and we can come together to make new discoveries, to have our glazes without borders. We have 3 presentations today from this online collaboration. Sue McLeod, who is a ceramics technician at the Art Center at Cedar Hill in British Columbia, was in my very first online class in 2014. And we talk every day, and Sue is going to talk about her discoveries that she's made with understanding cone 6 glazes. Kiara Matos is a potter originally from Venezuela and who lives in Connecticut. And she and I have been discussing the role of copper as an ingredient in our glazes. We all know it's a colorant, but we also know it affects our glazes. And we've done a lot of work to discover how and why it works. And Peter Berg on the end is a ceramic engineer out of San Francisco. And we've been discussing what are the real questions about copper and toxicity. If you read a lot of books, there's a lot of questions, a lot of, well, this is bad. And for me, the question is always why? Because we don't know why. We're ceramicists or ceramic engineers, but we're not toxicologists. So Peter and I, along with an actual board licensed toxicologist, have been studying what are the real effects of toxicity and copper. So we have 3 amazing pieces of information. So we're going to have everybody do their presentations, and then we'll have some questions at the end. So without further ado, please welcome Sue McLeod.
Okay. Can everybody hear me? No? Okay, I'll talk louder. Okay, thank you, Matt. So hi, everyone. I'm Sue McLeod. I come from Victoria, BC, where I work full-time as the ceramic studio technician at the Art Center at Cedar Hill. I also teach glaze workshops on the side, and in my spare time, I make pots and I test lots of glazes. I first started working with clay in 2008 at Kootenai School of the Arts in Nelson, BC. At that time, they offered a 2-year diploma in clay. In first year, we didn't make our own glazes, which sort of sucked, but was sort of okay because I was still making pretty crappy pots anyways. But then in second year, we had a glaze technology class where we learned a bit about the materials, but we tested hundreds of glazes. That class totally changed my relationship with ceramics. In high school, chemistry was my favorite subject, and I almost pursued it as a career, but I got distracted and I dropped out of college to travel the world. And I never really identified as an artist, I just always liked making things. Somehow, though, I ended up in art school, which was a bit weird for me until I got to glaze class. The science made the art so much more exciting. I was really enthusiastic about learning how to mix my own glazes because the process just looked so scientific. You wear a mask, which made it look dangerous and important, and you weigh out materials on a triple beam balance scale. It seemed so precise and mathematical, which really attracted me. By the time I graduated, I had a binder full of glaze recipes and boxes of test tiles. I had a good understanding of how to mix glazes and change their colors, but I still didn't really understand how all the materials worked together. Next thing I knew, I was out on my own and using my favorite glaze recipes from school. But they happened to be super runny at cone 6, so every firing was a gamble with fingers crossed that they didn't run too much. I became very proficient with a bench grinder. And then I ran into more problems like a kiln load where every pot with a certain glaze combination came out cracked right in two. I was losing so many pots and wasting so much time and not really learning anything. What were my options? Go back to school? Find new glazes? But I loved these glazes and I had so many of them. I just needed to learn how to adjust them. I know. I'll ask the thousands of potters on Facebook what to do. If any of you have ever asked a technical question in one of the ceramics Facebook groups, you might know what I'm talking about. I posted a photo of my kiln load of cracked pots and asked what I should do. I received exactly 65 comments, each telling me to do one thing or the other. Seriously, lower the lithium, add some silica, remove some silica, cristobalite, quartz inversion, change the heating rate, change the cooling rate. Don't open the kiln so soon. Compress, compress, compress. I was grateful for everyone trying to help, but it got me nowhere. I didn't know anyone. Who should I listen to? I was more confused than ever. It was a very short time later that I saw a Facebook post for Matt Katz's very first online Intro to Glazes course through Alfred University. I signed up and the course completely blew my mind. It answered all my questions, plus a gazillion other questions that I didn't even know that I had. That was in 2014. I've since taken Matt's Glazes 2 class, his Clay Bodies class, and I'm anxiously awaiting his next course offering. Fast forward to the present, thousands of test tiles later, I'm going to present to you the research I did on cone 6 glazes, their relationship with Stahl's glaze map, and how we can use Stahl's map to predict glaze behavior at cone 6. So Stahl's map, written in 1912, by the way, is a document that allows us to predict glaze behavior based on the chemistry of a glaze formula. In order to look at the chemistry of a glaze, we need to calculate the unity molecular formula, or UMF, of the glaze recipe. The UMF takes all the glaze materials in a recipe and breaks them down into the number of molecules, or moles, of each of the elements in the glaze. Every glaze will contain glass formers, and every glaze will contain fluxes. Fluxes are required to bring down the high melting temperatures of the glass formers. The glass formers are silica, alumina, and boron. Examples of fluxes are sodium, potassium, magnesium, calcium, etc. If you were to look at a periodic table of elements, the fluxes are found in the first two columns on the left. What the UMF does is it puts the glass formers into proportion with the fluxes. Chemistry is all about proportions of one element to the other. Once we know the UMF of a glaze recipe, we can plot it on Stahl's map, and we will be able to predict how our glaze is going to behave even before we put it into the kiln. You might be wondering how to calculate the UMF of your glaze recipes. There are various glaze calculation softwares out there where you just plug in your glaze recipe and it calculates the UMF for you. I recommend using the website glazy.org. That's glazy.org. It's free, and you can not only calculate the chemistry of your glazes, but you can upload photographs and share them with the ceramics community. It's also a great resource if you're looking for glaze recipes. Glazy.org will also take your glaze recipe and plot it onto Stahl's map for you. So Stahl's map plots silica levels on the x-axis and alumina levels on the y-axis while keeping the flux ratio constant. Flux ratio? What's a flux ratio? Well, there are two different kinds of fluxes. There are primary fluxes and secondary fluxes. The primary fluxes, also known as alkali metals, or R2Os, are found in the first column of the periodic table. They are lithium, sodium, and potassium. The secondary fluxes, also known as alkaline earths, or ROs, are mainly found in the second column of the periodic table. They are magnesium, calcium, strontium, barium, and zinc. The two types of fluxes work together. The primary fluxes get the melt going, and the secondary fluxes keep the melting under control. When looking at the UMF, the sum of the fluxes will always equal 1. Then we can further break down the fluxes and look at how much primary flux we have compared to our secondary flux. This is called the flux ratio, and it is generally written as a ratio of R2O to RO. Historical and contemporary research have shown that a flux ratio of 0.3 to 0.7 contributes to the highest durability of a glaze. As you can see, this is the flux ratio that Stahl used in his research, 0.3 moles of sodium to 0.7 moles of calcium. With a consistent flux ratio, all he did was vary the amounts of silica and alumina to create glazes at all points on the map. So, what does Stahl's map tell us? Stahl discovered that with a consistent flux ratio, a glaze's surface quality, whether it's glossy, matte, crazed, or underfired, is determined by the glaze's silica and alumina levels and their proportion to each other. Stahl predicts that glazes will be matte when the ratio of silica to alumina is 5:1 or below. As the silica to alumina ratio increases, the glaze becomes glossy. Stahl refers to glossy as bright on the map. Stahl predicts that glazes will be underfired at a silica to alumina ratio of over 12:1, and Stahl refers to underfired as devitrified. Stahl also predicts crazing, shown by hatch marks at low silica and alumina levels, the lower left-hand side of the map, as well as at high silica levels, the right-hand side of the map. Stahl's research was done at cone 11. For my research project, I recreated Stahl's map at cone 6 to see if the same patterns would exist at a lower temperature. Since I was working at cone 6, I couldn't rely on the fluxes alone to sufficiently melt my glazes. I needed to include some boron, which is a low-temperature glass former. This chart, written by Matt Katz, shows the relationship between boron levels and firing temperature. Based on this data, a consistent boron level of 0.15 was chosen for all of my tests, which is the ideal level for cone 6. For the project, I created 2 separate Stahl maps where I mixed a glaze sample for each point on the map and fired them all to cone 6. Here are the tiles arranged as if they were on Stahl's map. Each row represents a constant alumina level, and the silica increases from left to right. Map number 1 on the left has a flux ratio of 0.3 to 0.7, same as Stahl's original map. Map number 2 on the right has a flux ratio of 0.2 to 0.8. For both maps, I used sodium as the alkali metal flux, or R2O, and calcium as the alkaline earth flux, or RO. As I said before, all tiles have a boron level of 0.15, and the clay body used was Plainsman M340. It's a little hard to interpret my results just by looking at these photos, so I coded all the data and plotted it on Stahl's original map. I looked at each individual tile and decided if it was matte, semi-matte, glossy, underfired, crazed, crawled, or shivered. Here you can see the various trends that resulted at cone 6 and how they relate to Stahl's map. Matte glazes are on the left side of the map. Then as silica increases and you move to the right, they become semi-matte, then glossy, and eventually underfired when the silica level becomes too high. To make the results more clear, here is map number 1, 0.3 to 0.7, showing only the glossy results. Notice how they follow the general pattern and shape of Stahl's original map. This is map number 1 again, showing only the matte glaze results. This left-hand side of the map is where you will find true matte glazes, which are fully melted crystals growing in a glass. This is as opposed to underfired matte glazes that are only matte because they haven't actually melted yet. Often, these are underfired glossy glazes. If you have a matte glaze and you fire it hotter and it becomes glossy, the glaze was underfired to begin with. A true matte glaze fired hotter will run and it will stay matte. A properly formed matte glaze will be matte at any temperature. From a functional standpoint, you want to avoid underfired glazes because they are unstable and will break down over time. A glaze only becomes durable once it melts into glass. To make a true matte glaze, Stahl found that you need a low silica to alumina ratio, generally 5:1 or below. Look at the hard diagonal line of green circles that moves straight up the line that Stahl drew. This is the 5:1 matte line. My results line up exactly with the research that was done over 100 years ago. Science, very, very cool. All glazes on this line have a silica to alumina ratio of 5:1. As soon as the ratio went above 5:1, the glazes were no longer matte and started to become glossy. So, Stahl's map can be used to predict a matte or glossy surface according to the silica to alumina ratio. These tiles represent the 5:1 matte line that I showed you on the last slide. The tile on the far left contains 0.3 moles of alumina and 1.5 moles of silica. It would be plotted on the lower left-hand corner of Stahl's map where it is predicted that there will be crazing. As you can see, there is crazing. This sample is also running because the silica and alumina levels are so low that it's overfired at cone 6. With each tile moving from left to right, the alumina level increases by 0.05. The silica level is consistently 5 times the alumina. On Stahl's map, these tiles would move straight up the diagonal line of green circles from the last slide. As we move up the diagonal 5:1 line, increasing the silica and alumina proportionately, a couple things happen. The crazing is reduced until there is no crazing, and the running is reduced until there is no running. If we keep moving up the line, eventually the glaze dries up as it has too much silica and alumina to melt at cone 6. The results also show that there is a limit to how much silica and alumina a glaze can contain and still melt at a specific temperature, with a specific flux ratio and a set boron level. On both maps, when the silica to alumina ratio was above 12:1, the glazes were underfired. This behavior was also predicted by Stahl, where he calls them devitrified. I also found there to be a max alumina level, above which the glazes were underfired. That level changed according to the flux ratio. On map number 1, 0.3 to 0.7, the glazes dried up at 0.7 alumina. On map number 2, the glazes dried up at a lower alumina level of 0.6. This is because at 0.2 to 0.8 flux ratio, the glazes have less R2O, which is the more powerful of the two fluxes. Notice how the pattern of underfired is almost identical on both maps. The shape is the same, it just shifts on the map according to the conditions of what you're testing. If I were to increase the firing temperature, the whole pattern would just move upwards. There are some interesting trends with regards to crazing and thermal expansion. Crazing results from the relationship between a specific glaze and a specific clay body. Stahl's map was created based on his results with his clay body. These are my results with my clay body. Keep in mind that your clay body may give different results as well, but the general patterns are the same. When your glaze has very low silica and alumina levels, you're likely to get crazing. As the silica and alumina levels increase, the crazing starts to disappear. If you have a crazed glaze and you only increase the silica, you can move out of the crazing region, but you would then also be changing the silica to alumina ratio. Doing so would change the surface quality of your glaze, and if your glaze was matte, it could end up glossy. If your glaze was glossy, the transparency could change, or it could end up underfired. A better way would be to take your crazed glaze and increase the silica and alumina so that their ratio stays the same, and you will move out of the crazing region while maintaining the surface quality of your glaze. Now, let's look at the far right-hand side of the map, the high silica region. Map number 2 has some, and map number 1 has quite a bit of crazing in this region. This is because unmelted silica has higher thermal expansion than melted silica, so these underfired tests are also crazed. And the last most interesting thing to notice is that map number 2, 0.2 to 0.8, has a significantly lower number of crazed samples than map number 1. The reason being, sodium, the R2O flux, has a higher thermal expansion than calcium, the RO. Map number 1 has a higher proportion of sodium than map number 2, therefore map number 1 has more crazed samples. These two tiles are from the exact same point on the Stahl map. They have the same silica and alumina values, but different flux ratios. The sample from the 0.2 to 0.8 map has no crazing, where there is crazing on the 0.3 to 0.7 sample. This tells us that another way to get rid of crazing is to adjust the flux ratio, lowering the R2O flux while increasing the RO. The results from this research show us that we can use Stahl's map to accurately predict glaze behavior at cone 6. Stahl tells us if our glaze will be glossy or matte, crazed or underfired. This leads me to believe that Stahl's map could accurately be used to predict glaze behavior at any temperature, provided that your glaze is properly composed to melt at that temperature. Thank you. Please connect with me through my website or on social media. And now, Chiara Matos will present copper as a flux.
Hello. Is that good? Yeah. Okay. Hi, my name is Chiara Matos, and I'll be talking to you about copper as a flux, understanding the chemical role of copper on a glaze. Historically, colorants have been left out of glaze formulas. It was believed they didn't have an underlying role in the chemistry of our glazes and were not considered from a chemical point of view. Conventional wisdom, though, has it otherwise. Probably you have noticed in your studio or been taught or told by others that some colorants will affect your glazes by melting them, fluxing them, while others will have a refractory effect, like chrome, for example. In the case of copper, I have noticed, probably you too, that glazes with copper, a particular glaze with copper, will melt better than the same glaze without copper. In my online studies with Matthew, he brought up the notion of manganese and iron being documented to perform as ROs, or alkaline earth. Earths in the when considered from a chemical point of view in glaze formulation, and how they contributed when considered as such. This led him to believe that there was great potential in understanding the role of colorants beyond mere colorant addition. When he mentioned he wanted to do research with copper, I jumped in and offered to help. I have always been curious about the role of copper in the studio, especially after learning about R2O to RO ratio and how much it affects durability. I'm a functional potter mainly. So was copper flux in my glazes? And if it was, what exactly was it doing and how should I account for it? So we went ahead and tested. Our main hypothesis being that sorry, I'm having a hard time keeping track of this. Our main hypothesis being that copper was a flux and most likely an R2O, given how powerful it seemed to be as a fluxing agent, or how when in in the presence in our glazes. So we designed a test. Of course, keeping we stuck to the core of Matthew's teachings and what Sue just explained to you, which means using the UMF as a way to calculate our glazes, keeping an R2O to RO ratio, and using the Stahl map as a frame to our testing. So the way we started out was Matthew designed, he wrote a new UMF calculator on Excel that accounted for copper as one of the R2O fluxes. And we designed a formula with the least ingredients possible, which were copper as our R2O, sole R2O flux, calcium as our RO, flint, and then alumina. In some formulas, we were going to have too much alumina, so we used calcium kaolin to deal with viscosity of the suspensions. So, what was our plan? We would recreate a sample. We started with the first sample that would sort of fit a central area of the map, and if after we fired this sample, we plotted it into our Stahl map in accordance to what all the theory that Sue just introduced to you, it replicated the Stahl map results as predicted, then we were on the right track. So we did a first firing of tiles that had a 0.4 alumina ratio, and then we did increases of 0.5 silica, beginning with the lowest silica we could use. This is the first set of tiles plotted into the UMF. And I hope you can see it well. But as you can see, we have gloss tiles where we're supposed to have gloss. We have on the left-hand side where we have the purple dot, the tiles start to dry up pretty quickly towards the high alumina area. And then on the right-hand side, we have our last tile reaches just a 12:1 ratio, but as soon as we reach 12:1, the tile starts to dry. This is our first set. We think this looks great, so why don't we go ahead and cover a larger area of the map? And that's exactly what we did, and you can see it here. So we did 60 tiles total with a 0.2, 3, 4, 5, 6, 7 alumina level, which is on the right hand side, and then on the X right? I'm sorry, X, and then the Y, we have increases of silica. It's not. It's of course we moved up diagonally because the glosses are referenced to. Are they matting? Are they gloss? We wanted to stay on that gloss area, right? So again, gloss where we're that's the 60 tiles, and then we plotted them on the area that they represented on Stahl according to their chemistry, and their silica to alumina proportions. So again, we see gloss where we were supposed to see gloss. We have the purple border that that it represents the 5:1 silica to alumina ratio, and you can perfectly see how tiles start to get matte until they dry up, given the high levels of alumina. And then on the right-hand side, you have the red area that delimits our 12:1 silica to alumina ratio, and where glazes dry up again, given the amount of the excess of silica in the system. So what can we tell you? This was really exciting. And it brings us to the next conclusions. Copper is in fact a flux. Most definitely an R2O. I mean, given the fact that this worked out so well and tiles represented the map so well, we eliminated by default the need of recreating this with copper being an RO. Also, the ability to melt glazes that well, it's characteristic of R2O glazes. Looking ahead, we really think there is more testing to be done. We need to figure out whether all colorants do this, which ones are ROs, which ones are R2Os. If they are, then we need to think about balancing those ROs, including colorants in our glazes for sure, including them in our chemistry. I have already started to do that. I did a test right before leaving, and including copper as an R2O in a glaze that I have been using for my long 20 years as a potter. It's never looked better. I wish I should have. It was too late to bring in a photo and show it, but it was very exciting. And this does arise some questions. I think the durability is kind of covered once we decide R2O, RO, and how much of that we will use. But then we have toxicity, which is a big one, right? And I'm going to leave that to our next presenter, Peter Berg. Thank you so much.
All right. Good afternoon, ladies and gentlemen. My name is Peter Berg, and I need to adjust my microphone. I'm here to talk to you about copper, its leaching and glaze durability. We've had some wonderful presentations that have built the framework for the study we have done. Closer. Okay, let's get right up on in there. I'm going to have to read off of my phone. My eyes are pretty poor. I can't read that screen. So the pursuit was to understand copper release from glazes. Currently, there are no U.S. regulations on how much copper can leach out of a glaze. Oh, thank you, AV guy. It's pretty good. He's fixing it on my screen. The EU, the European Union, is talking about setting some limits, but nothing has been established yet. We're looking at 10 to 15 years before they come up with anything. We're going to talk about the leaching tests that are used, what we do to determine the actual leaching levels of copper coming out of the glaze, and we're going to talk a little bit about copper's effect on the human body, and can we actually achieve any level of toxicity from the product that we make and use. A couple of past references. At NCECA in 2016, Matt Katz established that the lemon test, taking the slice of lemon and leaving it on your plate, is not really a relevant test. The only important information you'll gain from this is whether or not your glaze will fall apart. It won't tell you what will actually leach out of the glaze into your food or what have you. Current laboratory testing that's available, in the United States we use something called AAS, or atomic absorption spectrometry. That's always the hardest word. It's a 2-generation-old test. It's very finicky. It doesn't give accurate results. For what we were looking for, it wasn't suitable. So there are 2 other forms of testing done in industry. You have ICP-AES and ICP-MS, which we'll get into in just a moment. The test we have were 24 tiles, all at a constant flux ratio of 0.3 to 0.7, what was listed as our known most durable flux ratio. We did not include copper as a flux because we wanted to see what was going to happen to the durability. There are 3 temperatures we looked at: O4, cone 6, and cone 10. These are common ceramic temperatures that people work at. We've got glosses, we've got mattes, and then we've got 4 varying levels of copper: 0%, 1%, 3%, and 5%. One thing to note, there is not a bullet point on this, but the boron level does change based on the temperature we're firing to. As Sue pointed out, there's a level of approximately 0.15 needed for cone 6. For cone 04, we need approximately 0.5 moles of boron. So that was a factor in here. The test procedure that we use is very important. This is to simulate a worst case scenario. This is the maximum amount of material we can leach out of a given glaze. How it's done is we prepare a solution of 4% acetic acid, more commonly known as household vinegar, diluted down from pure glacial acetic acid to a controllable level. That acid is then placed on a tile or in a bowl with a plasticine wall built up around it. You measure the surface area of the tile you're testing or the bowl and the volume of liquid that you're actually using. The solution is left to sit for a period of 24 hours at approximately 24 degrees centigrade, plus or minus 3 degrees. It's a little hard to keep it at a constant temperature. This allows for a process called ion exchange to occur, where the hydrogen in the acetic acid can replace itself with a portion of the glaze surface, either the fluxes, the silica, the copper, what have you. We can then take that solution, the leachate, and run it through these test processes to actually count how much of what came out. And this is where things will get fun. We'll talk a little bit about ICP AES and ICP MS. ICP AES is inductively coupled plasma with atomic emission spectrometry. We'll just go with that. Essentially, you're taking a flame, creating it in a magnetic field to create a plasma, which is burning at ridiculously hot temperatures, vaporizing most of what's in that leachate solution, and then the AES portion, the atomic emission spectrometry, can count the amount of atoms, the ions, the copper ions that are floating around. It's robust, it's cheap, it's dependable, it's kind of suitable for routine analysis, but it's not the most precise. So you have ICP MS, which is inductively coupled plasma with mass spectrometry. I hate that word. Oh, it's the last time I'm saying it, I promise. There we go. Thank you. If you've watched Bones, I'm sure you've probably heard that a lot. They run everything through the mass spec. Thank you. It is delicate and expensive to run, but it's capable of some phenomenal performance. So when we sent our samples off to get tested, we actually came back with 0 results from ICP AES. But it was observed on the tiles that there was physical degradation as the copper amount increased. We knew that something was leaching out. So we had to upgrade our test protocol to ICP MS, the higher standard, and we began to get results. Here come the wall of numbers. Buckle in. It's a little much. So, the data. As you can see, each cell contains a sample set. Our cone 04 gloss, our cone 04 matte, our cone 6 gloss, our cone 6 matte, etc., etc. A couple of trends occur here. Going from 0% to 5% on almost all the samples, the amounts began to increase. The more copper there was, the more material began to leach out into the solution. If you look across the line, going from 04 to 6 to 10, the values increased as well. As the boron is decreasing, you were getting more and more metals release. The cone 6 data I know looks a little bit scary. As I mentioned, that equipment is a little bit finicky. I think this is either a statistical anomaly or an underfiring in the kiln. I can't quite be sure what. Keep that data in mind because we're going to use that later. There's nothing else really to say about this one. Oh, one note. I should have done this sooner. The milligrams per liter, that's the concentration of how much copper you actually get per liter of liquid in the vessel. We're going to get more fun. So these are small samples. A big question, I think, in industry and for potters as well, is how does that correlate to my actual piece? You know, I've got this small sample, it gives me a metals release. What about my large bowl, or my favorite coffee mug, or my crock pot, or pickle jar, or what have you? We can actually theoretically calculate how much metals release based off of the concentration of the leachate and the surface area and volume of the piece. That formula took me about 2 weeks to figure out. There you go, it's free. As the volume increases, you'll notice that the metals release begins to decline. The larger the piece, you would think, because you have more glaze available, more glaze for attack, that you get a higher number. But the inverse is actually true. The ratio of leaching solution to the surface area dilutes it down to lower concentrations. So your real highest values are going to be from your smallest cups. Kind of interesting, I think. The values for the metals release in this case were used from that cone 6, very, very high 970 milligrams per liter, scary range. But you can see as you increase in your vessel size, you're actually getting less and less volume. Toxicity. Here's where it gets more fun. The CDC sets a value of what the human body can actually process in terms of copper. They say that you can handle less than 550 milligrams of copper per kilogram of body weight per day. Every day you can process this material through you. The body will absorb a portion of whatever you ingest, and the rest will pass through. Use your imaginations. Not spelling that one out. We're going to use that high cone 6 value, the 970 milligrams, in our theoretical talk here, and a subject who is a 150-pound male who's drinking about an average of 3.7 liters of water per day. That particular individual, based on their body weight, based on the CDC limits, can handle 37,400 milligrams of copper per day. Go to the next one. These are the exposure calculations in the worst case scenario. I have to pull this up. Wall of numbers, man, every time. So once again, you see the same chart. As the volume increases, your metals release goes down. The liters that you would have to drink to reach your maximum exposure go up. Clearly a less concentrated liquid, you're going to have to drink more of it to actually hit any sort of exposure level. The actual metal per kilogram of body weight that you're taking in this theoretical example, our worst case is only about 47 milligrams per kilogram of body weight. The CDC lists 550. Our worst case, we are nowhere near any sort of danger threshold. There's an effect that can occur if you're so inclined to try this. I don't recommend it. It's an effect called hyponatremia. Some of you may be familiar with this. It's common in athletes who dehydrate themselves and then overhydrate very, very rapidly. I go on to that. Hyponatremia is water toxicity. You can actually poison yourself by drinking too much water. Medically, what's going on is you are diluting the salts in your blood system. salts in the human body work as an electrolyte. They allow your brain to function. They allow your organs to function. If you start depleting it, trying to drink more and more water, you'll go through different stages. Initially, you'll begin to get very sluggish. You'll move slow and tired. It's harder to move because your brain's not quite functioning as well. As you decide, no, I'm still thirsty, I'm going to keep drinking more, you'll begin to get confused. You'll disorient yourself. If you continue drinking, you could, fall into a seizure. If you're so inclined to try to fight past that, coma or death is technically possible. It's not very likely. I talked to a very good friend of mine who is an ER physician, and the only cases he's ever personally seen or heard of were food challenge people who do this as, hey, I'm going to drink this much water this quickly, and we're going to make this happen. Or people with, mental deficiencies where it's a compulsion, where they have to do it. In terms of, average person drinking out of their favorite mug, you're never going to, well, I can't say never. You're not very likely to actually drink that amount of water. So, I don't believe that you would be able to hit any sort of chronic or acute toxicity based off of the low values that you could actually get out from your glaze surface. Continue on to the flux ratios versus the metal release. This chart is very simplified but contains some very powerful information. So you've seen this before earlier. It's the metals release at the various percentages, but what we've included on the far right column is the flux ratio when you begin to account for copper as an R2O. When you do that, the flux ratio begins to increase. The higher that flux ratio, the more metal begins to get released. Sorry, I need to look this up because I can't see. Yeah, as the boron decreases as well, going from O4 to cone 10, you actually get a higher metal release too. And what that tells me is these O4 glazes are actually more durable than cone 10. They just need to be formulated properly, and you can achieve even stronger, even more durable glazes than you are at the hotter temperatures. And oddly enough, in a significant amount of cases, you have to exclude the cone 6 matte portion, but they actually performed better than the gloss glazes. That's peculiar, as matte glazes are not known for their durability. They're finicky, they're difficult to formulate, they're difficult to fire, but on our sample set here, we actually made them more durable than the gloss glazes. It's very, very exciting. So kind of the conclusions we've come to in this research. AAS, atomic absorption spec, is outdated. It's not worth using. Reach out to your labs if you're having your ware tested. Go for ICP AES. It's cheap and efficient enough. ICP MS is more expensive, but if you really want an accurate number, that's the tool to use for the job. Metals release is not high enough, even in our worst case scenario, to get anywhere near chronic or acute copper toxicity. It's not, in my eyes, a risk, or in the CDC's eyes, they're telling us we can handle more than that. You can't suffer acute chronic copper toxicity. You'll induce hyponatremia before you do that. Please, nobody go do that. It's not recommended. As our flux ratio increases, we notice that, metals release increases as well. Puts more importance on formulating your glazes properly for, the most durability you can achieve. Especially if you're making food service items. If you're doing sculpture, go nuts. Do what you want. It's fine. No one's eating off of sculpture, I hope. As the boron decreases, metals release also increases. So, if toxicity is a major concern in your work, I'd recommend trying to fire lower. Learn from Matt how to formulate, and then fire lower. It's pretty good. And in this case, matte glazes are more durable than gloss, which was very shocking. The last question I have, and I have some tests that are being run through my kilns right now, is when you account for copper as a flux, when you reset that ratio at a high percentage, say 5%, to a 0.3 to 0.7, what will happen to the metals release? I unfortunately don't have an answer for you at this moment, but in the future I will have some solid information, and I think that's where it gets real exciting. Can we make stronger, more durable copper-bearing glazes? I think we can. That's it for me. I'll pass it off to Matt Katz.
So thanks, everybody. I hope you appreciated our nerdery and diving into some serious questions about how we understand our glazes. The ability to predict glaze behavior based on every aspect that's going into them is a really, really powerful tool, whether it's using Stahl's map to tell us if our glazes are well fired or under fired, if our mattes are true matte, or just a straight up underfired texture, to be able to perceive copper as how it affects our glazes, because we know that it does, and to really help to understand what are those true issues with the underlying materials. So have to do a little bit of thanks. All of our families on the screen, Alfred University, my wife Rose Katz, who is the hardest worker I know, Sarah Urfer, our toxicologist at ChemTox Laboratory, Jackie Fisher, Derek O, who is the creator of Glazes, who is our other co-conspirator who's not up here. Glazes is amazing because all the predictions that Sue has been talking about are plotted right onto Glazes. So you plug in a glaze formula and it tells you what it'll do. It's amazing. Richard White at Lucidon Laboratories, Virag Shah at Kaiser Permanente, Jefferson Kirkland, and the Art Center at Cedar Hill. And if anybody has any questions, please use the microphone. We'd be happy to answer them. Nothing, John? Can you use the mic? Just, it's being recorded. It's right back there.
I have a couple questions. First one is, when is your next class then?
My next class starts on April 1st. You can go to ceramicmaterialsworkshop.com. And if you're looking for academic credit, Alfred University on June 26th.
Okay, great. Thank you.
Absolutely.
I didn't hear that.
Ceramicmaterialsworkshop.com. We have classes starting for the general public on April 1st. And if you're looking for academic credit, my online classes through Alfred University, I believe, start June 26th.
So say you're using a copper glaze that's high in barium and strontium on the outside of a cup, but you have a stable, functional white glaze on the inside. Now, would you guys consider that functional, or would you have the outside tested for leaching for the inside liner glaze? Say it's using fluid.
In general, if the interior surface is a neutral base without any colorants, it's fine. There's really not much of a concern because it is the interaction with food, not the superficial touching with our lips. That really depends on the solubility of the raw materials, and as they've been fired, it's generally not an issue.
Okay, thank you, sir.
Absolutely.
Have a good day, guys. You're
Thanks.
awesome.
Hello, Jeff.
Hey, Jeff.
So I have a couple questions. Was your the leachant, was that the acetic acid that you sent to the lab to be tested then?
I don't know if you have to push it.
Can you hear me? Oh,
No.
you can.
Well.
All right, I'll talk a little bit louder. We actually send off the samples to the lab, the physical tile samples, and they run the acetic acid there. Everything's controlled. There's a chain of custody.
Yeah. I wondered if you considered testing it with something. I mean, the reason you chose acetic acid, I assume, is because it causes a discoloration, and that makes you think that something bad is happening. But it seems to me that people are using, that water's, more often, the thing that people are using. And you talked about hyponatremia and stuff, but really you're talking about drinking vinegar and drinking that much vinegar rather than drinking that much water. And so kind of got me thinking about, are we testing the right thing by testing acetic acid? So
there was a fair amount of research done into this by Lucidian Laboratories years and years ago on the best possible choice for an acid to use. They tested various concentrations of acetic acid, various concentrations of citric acid, which seemed more likely to transfer materials out, and lactic acid, milk. They got very little results out of the lactic. The citric acid, it depended on what it was bound up in. They tried to test tomato paste and they got 0 results from it, but they used diluted citric acid and they got higher results. It was too erratic for them to say you get a consistent result. So kind of the industry standard is acetic acid.
Okay.
Now water is going to have a lower I don't even think it has any sort of ion exchange, acid degradation. I've never heard of that, but yeah, you are absolutely 100% correct. To actually get the metals release, you would have to drink 48 liters of vinegar.
All right,
Please don't
thank
try
you.
it.
I had another
Don't do it.
question. The Stahl things, I love Stahl, and I fell in love with it, right? But your stuff didn't match up exactly to Stahl. Can you improve on Stahl, or can we better understand these lines? Because, it seems like all the recreations of Stahl I've seen are always looking at just the one part of it. They don't tend to go up as high, and all these lines are straight, and they look like rays that go on, to infinity. But I think you guys have come further along than just to agree with Stahl. I wanted your opinions on that.
Well, there is an upper limit to how, once we get to the upper parts of Stahl, then our glazes become underfired, and so as we go further up, like in alumina or silica, then we're not really testing anything that is functional. So the patterns of Stahl kind of stay the same. So we have the same pattern, and it can move around according to your flux ratio or your temperature. But the general shape and the patterns where it goes from matte to glossy to underfired stay the same.
Yeah, I saw that, and then but the lines were a little crooked, and that's what I was kind of wondering is what does that mean? That your line was a little crooked, or that. And I wondered if you thought about looking into that, because sometimes the interesting thing is the anomaly.
The problem that we found is we are discussing a redraw of Stahl, a highly intensified redrawing of Stahl, because there are definitive anomalies. It makes it look like everything melts. And what's really important about all of this is that Stahl works, but if you took those same tiles and melted them at cone 6, everything would be dry. It would be matte, underfired, whatever you want to call it. And so what Sue has done with the addition of boron is that it allows us to reposition Stahl at different temperatures. Well, there are tricks that we can do of moving to higher silicon alumina levels, which Stahl imply works. Well, they do work, they just work at higher and higher temperatures. And so we are discussing addressing those anomalies in a new version. It's just quite an undertaking for people that have relied on this for 100 years to sort of go, oh, well, we know better now. But, we're sort of figuring it out.
Thank you so much.
Thanks, Jeff.
Thank you.
This is more of an administrative question. Will you be making these presentations available online?
Yeah, you can go to our website, ceramicmaterialsworkshop.com, after the conference, and we'll have links, PDFs of the write-ups and the presentations.
Great, thank you.
Absolutely.
What lab do you use for testing?
I use Lucidian Laboratories. They're based out of Stoke-on-Trent in England.
What was it called?
Lucidian,
Oh.
Lucideon.
Yeah, but that's shipping to
Yep.
Yuck.
The issue that we found is, unfortunately, the one major lab in the U.S. that advertises pottery testing, if you go online, you'll find a list of places.
Right.
None of them exist anymore.
Not even Alfred?
No, the Alfred Analytical Laboratory has been gone for a very long time.
Okay.
The one place that is still open is Stony.
Stonewater?
No, Stony Brook. Oh my God, I'm even forgetting.
Something Brook.
Anyway, the problem is they use the AAS standard. And working with our toxicologist, that AAS standard that they're using is 2 generations old, and is no longer considered adequate for basic groundwater testing, which is where a lot of our testing procedure comes from. So with working with our toxicologist, she highly encouraged us to work with the ICP AES and the ICP MS. And that's basically because we found 0 results in the ICP AES standard. That actually sort of shows the failure of the test, because there was copper, but if the test isn't good enough to show it, then the test doesn't do you any good.
Okay. And then my second question is, did you find that the level release of copper went up with dishwasher as there was, cross hatching on the piece?
We didn't test the dishwasher. That's a whole different type of chemical attack.
Yeah.
That would be an interesting maybe next year.
Okay.
Well, we have one other thing that didn't come up, but working with the toxicologist, we ran the numbers of how much copper is in the glaze to coat the inside of a regular 12-ounce mug. And the problem is, at most, there is actually less copper in that glaze than you could even extract to get 1 kilogram. That 1 kilogram, about the size of a lab rat, wouldn't even hit their maximum exposure.
Okay.
And you'd have to extract 100% of that copper in that glaze.
Okay. Thank you.
Yep. Hey, Kevin.
Hi. I had a few questions about copper as a flux.
Mm-hmm.
What was it that sort of initially suggested that it was an R2O flux instead of RO? And my other question is how is there sort of a one-to-one relationship between like copper and say like sodium? Like for example, like is 1 mole of copper equivalent to 1 mole of sodium, or is there, a slight difference?
So the first one is how powerful it seems. Only R2Os will be so powerful a flux. And then when we got the results and it all fitted so nicely on the map, I don't know if you want to add anything to that.
We did the first test just as R2O, just conceptually, and because the model fit perfectly, if we tried to run it as RO, it just wouldn't even work because everything would have shifted and the map wouldn't have been recreated. But the fact that we perfectly recreated Stahl's map using only copper, and again, gotta emphasize that was the only alkali metal flux in that glaze. There was 0 sodium, lithium, or potassium. It was only copper and calcium in that glaze. And it perfectly recreated, and so we were sort of satisfied with that result.
And then the other thing for your copper to sodium, I mean, the UMF calculator will do that for you, but how much if you want to.
Yeah, I mean, we can. It's not integrated into any publicly available calculators, so I think on some you can choose which materials are represented as such, but it definitively should be. There is one effect that was up there and that we didn't particularly note, but that Kjar's map was fired at cone 6, and that copper, we believe, is just a more effective flux in the same way that lithium will fire a cone or so lower under sodium, which is under potassium. And so copper is just more powerful, but from a fluxing ratio, like 0.3 to 0.7 still holds, and all of that.
Cool, thank you.
Yeah.
Yes, I think that hyperglaze will include copper in the calculation if you don't put it in the colorant area and you put it in the glaze recipe itself. I'm not sure. I'm trying to picture it in my mind and I can't. I'm wondering if there's any data. I don't know how alkaline food can get before we stop eating it, unless it's lutefisk or something. Or that cheese that they roll in wood ash. But I wonder if there's any data that compares alkaline water to acetic acid in leaching tests. I know dishwashers are way over the limit and they really beat things up, but I'm wondering if there's anything that compares it one way or another that you know of.
Hold on, Peter, before you answer that. So we're over 5 o'clock, and Core and Evan, I see you guys, and I'm so happy. But we can talk at the back of the room just so that we can let the AV crew go after Peter answers. But we're more than happy to hang around outside and answer questions all night long until my wife drags me away because I can glaze nerd with the best of them. But Peter, go ahead.
To answer your question, I've not seen any data that makes that correlation. It's just kind of thinking about the whole dishwasher thing. There are detergents that are pH balanced. I'm doing a little bit of research into that now, but the dishwasher might not be so scary as I once kind of thought it was.
Although from all of my previous durability testing that I published in 16 and 12, that was all dishwasher based, and can be very corrosive if the glaze formula is in an undesirable range.
That still holds true.
Yes.
Yeah.
All right. So we'll be happy to hang around outside. Thank you everybody for coming.